And also, I think homework 3, there's a question that I like. That is about the partition function of the hydrogen atom. And I think it is a good exercise to think about what happens when we try to write down the partition function for some states with infinite energy levels. So try to think, but if you have questions, just ask the TAs or me. Okay. So I think we'll start today's lecture. As usual, we'll start from reviewing what we have done before. Okay. So there are several important concepts that we try to went through, and one of them will be directly related to one of the homework problem. Excuse me. That's basically about the ergodicity. In the last lecture, I mentioned some of the very interesting topics related to the issue of ergodicity, because in principle it is really a theoretical concept that require more mathematical manipulation. But I think it is not really necessary for us to went into that direction. So I'll just explain things in human language about what is the meaning of this ergodicity idea. So basically, as we mentioned, that what we are trying to study is basically a many-body system, or a system with many degrees of freedom, and we try to describe it in the phase space. Within the phase space, there are some constrained regime. Let's call this thing the phase space. And usually, the most important constraint for the system that we considered so far is the energy must be conserved. So this is the okay. So what that means is that within this phase space, we might have various different configurations about our system, but the point is that every point basically represents the status of the system has the same energy. So that space is basically the constraint space that we are interested in. So another way to think about ergodicity is that maybe our system belongs to one of the initial configuration that is represented by a point in this constraint space. And then as the time evolves, this point will start to move within this space, right? So in principle, as the time evolution is really, a long time evolution, you'll try to explore all the possible regimes, in this constraint space. Okay. And when we say the system is ergodic, what we mean by that is actually as the time is long enough, then we expect this system to explore all the possible configurations within this constraint phase space. So that's the idea of ergodic. So if the system can achieve that goal, we say the system is ergodic. But sometimes maybe the system cannot reach that goal. That is, maybe the system can only explore part of the phase space instead of the all the accessible phase space. Then the system will be called non-ergodic. So at this moment, we are studying the ergodic system, where we can try to consider the simplest case that all the possible microscopic configuration will be visited at the long time limit. So basically, that's the idea. So here I'm just trying to write down something that's more mathematical. So basically, we have already discussed the idea of observables. So suppose we have some physical observables. Maybe let's call it O. And in the experiment, basically the real world experiment, what we are trying to measure is actually to some extent the time average value for this observable O within the observation time. Okay. So what does that mean? It means that you just measure the system within some time resolution window of your equipment, maybe some time scale tau. And we know that this time scale tau is going to be a macroscopic time scale. And this microscopic degrees of freedom will just bounce back and doing some very crazy motions. So that time scale will be a much smaller time scale comparing with the observation time scale we did in the lab. Okay, so in that sense, usually what we measured is actually the time average effect of all this microscopic motion. So that's why usually what we measure experimentally is actually some time averaged physical observable values. Okay, so let me try to write it down in a more definite way. Okay, and this T is some macroscopic time scale. Okay, so now we define what is the time average value of the observable. Then what ergodicity meant, as I just described, is that we assume that this observation time is relatively long. So we are averaging over a very long time scale. And we said that this average over this long time scale is almost like you try to evaluate the observable through the microcanonical ensemble. Okay, so this equalities or this approximation is not always true. It is only true when we are discussing the ergodic system. Okay, so as we have discussed the concept of microcanonical ensemble, basically we said that in principle you need to average over all the accessible phase space, but we know that the dominant contribution is coming from the equilibrium configuration. Therefore, this expectation value actually will be the equilibrium configuration that we derived from the experiment. So here, what the idea behind is that the dominant. Okay. So that's basically how we try to bridge the two different concepts of time evolution average, which is the dynamics that we really care about, with the statistical description of our system. Okay. So so that's what I think something that I want to emphasize basically about the ergodicity. And then there's another question, maybe it's a bit tricky, is that a lot of the discussion we have done before, we need to have a well-defined concept about what do we mean by accessible phase space. Okay, so basically the first question is accessible by what, right? Like even though we have some degrees of freedom, but the Hamiltonian might be different, so it might have different kind of evolution. So usually when we say accessible, we are talking about a particular type of time evolution. Okay, so in the previous discussion, we usually use the canonical evolution, so we know what how the system evolved as a function of time. Okay, but so maybe I'll write it down. Okay. However, as we have discussed about the paramagnetic phase in the previous lecture, so let me try to remind you about the. Okay. So we said that, basically the degrees of freedom, you can think of it as some kind of binary degrees of freedom, that either it is pointing upwards or it is pointing downwards. So basically the Hamiltonian, when we apply an external field, can be written as the external field times the magnetization, which is the total vector summation of the individual magnetic moments. And here, this H represents the Zeeman field, that's pointing in the z direction in your spin space. And this mu I represent the magnetic moments, which, as we assume, it is going to be a binary object, which can point in the z direction or the opposite direction of the z coordinates in the spin space. Okay, so why do I mention this question? Because in this spin system, it is not obvious what kind of evolution we are considering. Okay, because it is not just like the usual particles that we know how things evolve. Okay, so the reason for that is because actually this is a very toy model like assumption, and we assume that the vectors of the little moment can only point in upwards or downwards. But in real life, these magnetic moments at the atomic scale, they can point in arbitrary direction. Okay, so because we make this very crude simplification, so the dynamics for this system is actually not well defined. Okay, at this moment when we just write down the Hamiltonian, or when you just write down the Hamiltonian, you should expect there's no dynamics, because at this point, once you give me a configuration of the spin, you just stuck there and just tell me that what is the energy. So when we are doing the calculation, we kind of have a rough assumption in the back of our mind that these spins can actually go from one spin configuration to the other configuration through some kind of microscopic process, maybe thermal fluctuation or things like that. But we did not really specify that. So when you try to think through this model, maybe you'll feel confused. What do we mean by evolution in the phase space if I just look at this Hamiltonian? But I'm just trying to tell you that this is just an example that's useful to demonstrate the idea about what are the accessible configurations using these binary variables. But if you think hard enough, you'll realize that there are some other additional information we should provide in order to define what do we mean by accessible. Basically, you need to tell me what is the evolution, what is the rule that governs the evolution for these microscopic degrees of freedom. Okay, so those are the two ideas I think that worth mentioning. And in the last lecture, we basically talk about the microcanonical ensemble, which means that basically means that we try to fix the energy of our system. Okay, and then we ask what are the possible configurations that is compatible with this condition. And then we said that we just assign equal weights for each microscopic configurations. So we assign and we use C to denote it. So the expectation value or the average value of the observable then can be calculated easily. At least formally, maybe it is not easy, but formally you can calculate it like this. Okay, so what it meant is that you consider all the microscopic configuration C, and within some phase space volume that's represented by this gamma, and then you just average over the observable A that you are interested in within that phase space volume. And what is outside here is just 1 over the phase space volume. And the reason that you have this 1 over phase space volume is because you want to have a normalization condition. Because if you try to rewrite this thing in another way, it actually should look like this. Okay, so what that means is that you want to evaluate the expectation value of A with the probability P of C, which is the microscopic probability for the microscopic configuration C. And by comparing these two expressions, then you can see that this probability actually is just simply 1 over the volume of accessible phase space. And the reason of that is because it is just a restatement about we want to assign equal weights to all the possible microscopic configurations. Okay, so that's basically the canonical ensemble, and we try to use a very simple model. That's basically the ideal gas model, where we can do everything exactly to evaluate what is the volume of the phase space, and starting from there, we can get the expression for entropy, and then knowing entropy tells us that we can derive the corresponding physical observables like pressure and other things. Okay, so that's basically what happened in the microcanonical ensemble. And then we mentioned about the canonical ensemble. So the concept of canonical ensemble is basically very similar with the Legendre transformation that we have done in the thermodynamic potential. So let me try to make a comparison. And canonical ensemble. Okay. So microcanonical ensemble tells us that the energy is fixed. But sometimes, or like in the lab, usually we cannot fix the energy. Instead, what we are doing is that we try to take a big reservoir with certain temperature, and we try to use that reservoir to have some energy exchange with the system that we are interested in, so that we set the temperature of our system to be a fixed value. Okay, so usually in the lab, what we are more interested in is about the situation where the temperature T is fixed. Okay, so so the thermodynamic potential at the microcanonical ensemble, to some extent, you're talking about the energy, but after you do the Legendre transformation, then you got the Helmholtz free energy. Okay. So how the idea goes? So basically, we have discussed that. Let me just try to remind you the argument. So basically, we have a big reservoir. Which has a fixed temperature T, and we try to have a make a thermal contact with our system that we are interested in. So here, the thermal contact means that the system can exchange energy with our big reservoir. Okay, and also we are considering the isolated system in the sense that the reservoir and the system, which form a composite system, cannot exchange anything with the rest of the world. Okay, so if we try to consider this system, and then we try to think about the microcanonical ensemble that we start with. So basically, the energy for the system and the reservoir will be a constant because they did not exchange anything with the rest of the world. So we expect we can evaluate the equilibrium value of our observable to be described by this. Okay, so this is just the microcanonical picture. for the system and the reservoir. Okay, so let me explain every term. So because we care about the expectation value of the observable that is defined on our system, so according to the microcanonical description, we want to average over the value of this observable using the microscopic configuration of the system, which is described by this KCS. Okay, so you just evaluate this quantity within all the possible phase space that is accessible by the composite system, which now contains the system that we are interested in and the reservoir. So that's why you need to integrate over to a microscopic configuration. One is the KC system and the other is KC reservoir. Okay, and then now the total phase space volume contains two parts. One contribution is from the microscopic configuration of your reservoir, and the other is the microscopic configuration of your system. Okay, so that's basically what this equation is telling us. So we can simply re-express this this integral by noticing that we have the constraint that the total energy of the system and the reservoir must be conserved. So we can do that by re-express this integral. Now we integrate over the microscopic configurations of our system and the microscopic configurations of our reservoir. But now we use the delta function to include only these configurations that satisfy the fact that the energy of the reservoir and the system must be summed up to a constant. Okay. So going from here to here is just simply re-express the integral using the delta function. Okay, this delta function, as I mentioned in the homework, it acts like some kind of if statement. Yes? That's a very good question, because in principle, yeah. So one question is, so the question is why A is only depends on KCS. Okay. So let us try to think about what A is, right? So A is some observable. So let's try to think about what kind of observable we have. We could have energy, we could have volume, or we can have some other things like particle number, etc. Okay, those are the observable. So what do we mean by average value or the equivalent value of those observable for our system? So it means that we are trying to evaluate the energy of our system. So the first question is, if we want to evaluate the energy of our system, can it only depends on the configuration of the microscopic degrees of freedom of our system? That's the first question, right? So suppose we are thinking about consider the following two scenarios. Okay. So here's our big reservoir, and suppose we have some particles in our system. Okay. And we care about the energy. So in this little system, the first thing is like what kind of energy we had. We have kinetic energy, for example, like pi squared divided by 2m and sum over I, right? So this kind of thing is the total kinetic energy. Then if we just focus on this term, it is to some extent obvious that we only care about the microscopic configuration of the system. Because in the environment, we might have some other degrees of freedom, maybe some other particle is moving around, but the kinetic energy of those particles is not part of the system's kinetic energy. So if we only focus on this term, then it is okay that A will only depends on the microscopic configuration. Okay. But it is not always the case, because the system could have some interaction between the microscopic and the macroscopic and the reservoir. In principle, it should have things like that, because if there's no interaction between the reservoir and the system, there's no way they can exchange energy, right? So in principle, this term exists, but as we discussed in the previous situation, we kind of assume that the system and the reservoir can interact with each other, but to some extent, they still remain statistically independent. So, so one conceptual way to think about that is that they can exchange energy through this term. However, this interaction is very localized to some extent. This interaction term only is important when the particles are nearby the contact, so they can bounce with the wall and exchange energy. So but you know that in this system, most of the particles are not nearby the wall. Only, very little portion of the particles will be nearby the wall. So only for those particles, this interaction will be important. But as we mentioned, we care about the thermodynamic limit. That means that this part of the interaction usually is very weak, so you don't need to worry about them. So in that sense, whenever you want to discuss the observables, usually you have two parts. One is the part that you can have a well-defined meaning with only this the degrees of freedom in the system, but there are also other parts that related to some kind of interaction in this way. But there's an implicit assumption that we assume that the interaction we are dealing with now is only short-ranged. To some extent, they only can interact with the reservoir nearby the boundary. So I think there's another example I've mentioned. For example, in the case of this gas model, usually the interaction is some kind of short-range interaction. They only see each other when they bounce with each other. But if you consider charged particle, then you will have some kind of Coulomb interaction, like I think if it is potential, it should be R. But anyway, if you have Coulomb interaction, then you will have this type of long-range interaction. What does that mean? It means that even for the particle that is at the very right end of our box can still feel some finite amount of energy with the rest of the reservoir. So in that case, this assumption might not hold. So we implicitly rule out this assumption, this kind of situation. So that's the reason behind why we can focus on this type of expression where the observable only depends on the microscopic configuration of the system. Okay, so that's a lot of explanation, but I think that's a good question, so I'll just explain more. So does that make sense? Are there any other questions about this part? Okay, so if no, let's try to move on. So basically, from the first line to the second line, we just rewrite the integral. Okay, so not much is done at this moment. This part, I'm trying to say xc is well defined. Okay, that's a side remark. Okay, so now once we rewrite the integral, now we have a delta function in our integral, right? And at this moment, we can try to ask ourselves, what is the meaning of this delta function when we try to integrate over the CR? So CR is like the microscopic configuration of our reservoir. So we are counting the volume of the phase space for our reservoir according to the rule that's given by this delta function. And because of that, we can relate it, or we can just re-express what that means. It means that we are trying to calculate the volume of the phase space volume of our reservoir that satisfy the condition that the energy of the reservoir is basically the total energy subtracting the system's energy. Okay, so that's another way to interpret this delta function. So we can try to think about why it is so, because when we integrate over the microscopic configuration of our reservoir, what we are doing is actually we are changing the expression of HR of CR, right? So different C will have different energy HR. But the delta function tells us that only the contribution such that the argument is 0 is counted in this integral, right? So in order to make the argument to be 0, that means that the system, the reservoir's energy must be equal to the total energy of our composite system, subtract the system's energy. Okay, so that's why this integral can be considered as the phase space volume of the reservoir, but with the specific energy that's given in this argument. Okay, so at this moment, it seems like it is again we try to say the express the same integral by using a different language by the phase space volume. But why do we want to express it in terms of the phase space volume? Because we know that there's the Boltzmann postulate such that we can use it to simplify or to approximate our system. So now if we use the Boltzmann's postulate, then we will have this expression now the phase space volume will be re-expressed by the entropy of our reservoir, but with the energy that's specified to be the total energy subtract the system's energy. Okay, so at this moment, this is just using the Boltzmann's postulate. Okay, so now we should be able to notice that because the definition of heat baths is that it must be larger compared with the system, okay, or the reservoir needs to be much larger compared to the system. So the total energy must be a quantity that is much larger than the system's energy, okay. So once we know this information, we should be able to expand this entropy expression and see what we can get. So eventually, what we found is that we'll just do the expansion. Let me just write down everything. Here we just do not touch anything in the CS, and then we just do the expansion around the total energy. So we will have the first term is okay, and the second term is this derivative evaluated at E total times the system's energy that's determined by the microscopic configuration C. Okay, yeah, maybe I should plus the rest of the stuff, but because the rest of stuff is like high order correction, so we basically drop it. Okay, so at this moment, we should ask like, what does it, really help us to understand the system? So the first thing is that we notice this total energy of the reservoir is basically independent of the microscopic states of our system. So you can pull that factor out. So it is not important to some extent. And then here is still the phase space volume. So another thing is that we can look at this quantity, which is the entropy, taking a derivative with respect to energy. And from the previous discussion, we know that this thing is basically the 1/, temperature that is defined by the reservoir. So if I include this information, then the above integral can be expressed or can be approximated in this way. Okay. So at this moment, we can see that maybe there are some factors in the front, but the key or the important concept here is that we are trying to get some expression that looks like this, where P of Cs is the probability for the microscopic configuration. And we are almost there after we did this approximation, because now we can tell that the probability of Cs should be proportional with this factor, which is related to the energy for a specific microscopic configuration, Cs. Okay, so the whole point of this derivation is to explicitly show that the probability is proportional to this factor, which is called the Boltzmann factor. Okay, and the rest of the stuff in the integral, in front of the integral, is just some kind of constant. So whenever you try to normalize your probability interpretation, you know that this constant is not going to be important. That's basically what we did in the homework one. Whenever you have some probability distribution proportional with some factor, then you know how to construct the normalization factor. So you can do that, and eventually the important you can try to figure out the constant, and then the important thing is that the probability of the microscopic configuration can be expressed by this. Okay, and here this z is called is the partition function, and in the microscopic it is related to basically the normalization condition of this weight. Normalization condition for the probability. Okay, so here we are assuming that the microscopic configuration Cs is a continuous variable. So if it is in the discrete version, one should take the discrete sum of all the possible microscopic configuration Cs, but with this Boltzmann factor. Okay, and this thing is called the this is the partition function. This is the continuous version, and this is the discrete version. Okay. So I think now it is a good time to make the comparison. So basically, I think this is the probability distribution for the canonical ensemble, and for the microcanonical ensemble, the probability distribution is basically just 1 over the phase space volume, because every microscopic configuration is considered to be equal with each other. Okay, so now we went through two very important ensembles. One is the microcanonical ensemble, and the other is the canonical ensemble. So now let's try to make a further connection with the thermodynamics that we are familiar with. So as we just discussed, the expectation value of any observable A now can be expressed by this way. And here, this could see are all the microscopic state for our system, because we now will only focus on the system. So I will just ignore the sub-index S. Okay. So so we can re-express this integral by saying that we want to sum over the microscopic configurations through the energy variables. Okay, so let me just finish this line and then we'll take a break. Okay, so this line is basically doing nothing. Basically just says that we want to collect the information through the energy. And how do we do the collection is that basically if you integrate out this E prime, you'll find that because of this additional delta function, all you need to do is to replace the E prime in the exponent by this h of c. So we will start from here in the next lecture and try to build a connection with the thermodynamic potential, and then we'll try to say more about the general concept for ensembles. Okay, so I think that will be it. See you in 2 minutes. Okay, so I think we'll continue our lecture. So I think there's one important question. I'll try to explain that a little bit more. So the question is about what is ensemble. I think that's a very important question. So so basically we can see now we have introduced two types of ensemble, but I'll discuss a general idea how to construct the ensembles in various different cases. But the point is that in the microcanonical ensemble, we said that we assign a probability distribution for each microscopic configuration such that it has equal weight. And the reason we can make this assignment is related to the fact that when we consider the phase space volume, when the system is isolated, remember that we said that, most of the phase space is going to be contributed from the equilibrium configuration. So because of this, when we average over the whole system with equal weight, it will be almost identical with the expectation value or the average value of our observable. So that's the way we justify why microcanonical ensemble makes sense. Okay, so but when we try to step back and think, okay, so what exactly is this microcanonical ensemble telling us? The most important thing is that it tells us what is the probability for the microscopic state. And in this case, it is trivial, just everybody is assigned equal weight, okay? So now we ask the second question. In real world, there's no isolated system. So to some extent, this microcanonical ensemble is not really practical in some sense. So we can try to think in the lab what kind of parameters that we can control. So most of the time, or maybe one of the most important parameters that we are able to control is the temperature, right? So instead of consider a fully isolated system, maybe it is more practical for us to think about the system and try to construct the probability of the microscopic states under the condition that we want to fix the temperature of our system. Okay, so the question is, turns out if we know microcanonical ensemble is the way it is, can we use this concept and generalize it to find a description of the probability of our microscopic configuration with fixed temperature? Okay, so what we are doing in the last course or in the last lecture is basically we are trying to went through the argument. We said that at first we used the assumption that we assume microcanonical ensemble's picture works. That's basically the first line of the equation. And then we said that, oh, here we need to consider the summation over our phase space, right? But this phase space is restricted to the fact that the reservoir and the system's total energy must be a constant. Okay. Then we said that this integral, if we try to stare at it and try to think from a different perspective, it is related to the phase space volume, okay, of our reservoir. But now it is with the specific energy constraint. Now it's not restricted by the total. Now it's restricted by the total energy and the system's energy, because we know the sum of the system, sum of the energy of the system and the reservoir must be constant. Okay. So once we have this interpretation, then we said that, oh, this interpretation is nice because it allows us to use the Bosons postulate to connect the description of the phase space volume with the entropy, which is the thermodynamic quantity that we are more familiar with. Then we got this expression where you can see there's an exponential factor in the integral. Okay, and what's the advantage of doing that is because from the starting, we assume that the reservoir is huge, which means that we are able to make approximation by assuming that E total is much larger than the energy of the system. Then we start to do the tidal expansion, which is our friend. Then we realize that after this process, the important information we got is that the probability distribution of the microscopic configuration under the fixed temperature condition now is proportional with the Boltzmann factor. Okay, so that's the goal basically we achieved, and it tells us that once we know how to describe the weighting for each microscopic configuration at the fixed temperature, then we should be able to make various prediction, like the mean, like the expectation values or the variance or all kinds of stuff we want. Okay, so that gives us basically the full information of our system. Okay, so and we said that this ensemble, under the condition that temperature is fixed instead of the energy is a fixed quantity, is the canonical ensemble. And the most important information for canonical ensemble is that it can give us the probability description for the microscopic state under the fixed temperature condition. Okay, so I think that's what we have done in the past 15 minutes or so. So I think I'll try to continue, but before that, are there any other questions? Okay, so if not, let's try to continue. So in the end of the last lecture, I tried to express what is the expectation value of an observable A. So you can see that this expectation value is simply something that we are familiar with. You just evaluate A with the weight that is proportional with the Boltzmann factor. Okay, and now I'm saying that maybe we can try to look at this integral in another fashion, that you can try to include the states with a certain energy E prime, And at this point, this E prime is quite arbitrary. But the point is that if you try to do that, then you need to have a delta function to restrict it back to the condition that you start with. So if you just integrate our E prime, you can see that this expression is identical with the expression that we got initially. Okay. So the question is why it is useful if we want to do things like that. And the reason is if you just look at this part of the integral, you will see it is almost like we are doing the microcanonical and ensemble for the observable A, where the energy is fixed at E prime. Okay, so this integral should be proportional to the equilibrium value A at the energy E prime from the microcanonical ensemble picture. And this line is basically the canonical ensemble. Okay. So actually we can do even better because we know that every configuration is assigned with equal weight in the microcanonical ensemble. So this integral should actually be something like the equilibrium value of A evaluated at energy E prime times this times the volume of the phase space, which is the entropy at E prime divided by KB. Okay. Again, this is the Boltzmann's postulate because we know the weight is assigned to be equal in this microcanonical picture. Okay, so let me try to write another line, then you'll see why it is an interesting expression. Maybe I should write TS. People is more used to TS. Okay, so here I'm just re-express the whole integral by combining the exponential factors. Then once you combine them, and you will see you basically get an expression that's very similar to the thermodynamic potential or the Helmholtz free energy that we are familiar with. So the form looks similar, but at this moment it is not. We are still not there yet. Okay. So in principle, we are, in order to evaluate the expectation value of our observable A, what we need to do is that we need to perform this integration. Okay. And at this moment, we should be, a little bit sensitive about the exponential factors, because we know the first thing is that